Today's presentation is titled Cavity Filter Design Using HFWorks for SolidWorks. Okay. Now, just a few housekeeping items before we get started on this webinar. Before we progress towards what the agenda for today is. As Adam mentioned, this webinar will be recorded and you will be sent a link to it. So please feel free to view it later or share it with your colleagues or friends who could not get a chance to attend this webinar. Okay. And the second thing is, any time during the webinar, you're welcome to ask us questions. If you refer to the GoToMeeting chat section, please type in your question. You can just enter it as a message, and towards the end of this webinar, me or one of my another engineer who is supervising this webinar, whose name is Ben, one of us will be very happy to answer your question. So we would love this to be an interactive session, but due to the way the webinars are done, this is the best we could do. Is please feel free, as and when you have a question, to type it in here. We'll do our best from our side to cover it at the end of the webinar. Okay. Having said that, welcome again, and we will move towards what the agenda is for the day. Okay. I'm going to start with talking a little bit about HFWorks. You know, what that product is, what it can do, what are the different kinds of industries and applications that it can tackle, and so on. Okay. Then we will move on to some of the capabilities of the product. Okay. Then we will get into the topic for today, which is cavity filters. Let's see what are the key issues that designers of cavity filters face, and how HFWorks will be able to help with designers who design these cavity filters. Okay. Then I will be showing you a live demonstration using a cavity filter example that was created using SolidWorks. It was quite an interesting model, and we will take a look at that. Okay. And finally, we'll get a chance to answer some of your questions that you wish to type in during the chat. Okay. Now let me start with about HFWorks. Okay. HFWorks is a gold certified product of SolidWorks. Okay. It is a 3D field simulation software that is basically able to help you simulate your RF and microwave devices. When I mean RF and microwave devices, I'm actually talking about passive devices. Okay. HFWorks is fully integrated inside SolidWorks CAD, so that allows users to quickly create their CAD geometry of their passive RF and microwave components and simulate them simultaneously inside their CAD using HFWorks. Okay. As I said, it's a gold certified product. That means the look and feel, the documentation, etc. will be very similar to your SolidWorks CAD. So for those of you who are well used to SolidWorks CAD and who've been designing using SolidWorks CAD, learning this tool or using it to do your simulations is going to be extremely easy. Okay, it's easy to use, as I mentioned here. It's certainly very friendly and similar to SolidWorks. It's accurate and powerful, and the beauty about HFWorks is it's a light add-in product, yet one can use it in a desktop, in a laptop, and so on. So you don't really need very powerful Unix type of machines to run this product. So it's a Windows-based desktop solution for SolidWorks. Now, when you look at the HFWorks capability, it's mainly, we focus on three specific phases, types of simulation. Okay. Antennas form a great category of products that are designed today in the RF and microwave world. We'll have future webinars which are dedicated to antenna simulation, but HFWorks can do antenna simulation. The next type of simulation that HFWorks can do, which really caters towards all broad classes of RF and microwave products, example filters, couplers, combiners, etc., is the S parameter simulation, where the product gives you the S parameters of your device. And finally, you can also look at the resonance frequencies with which your device operates using the resonance simulation. As far as today's concerned, we will mainly deal with S parameters. However, I will also show you some resonance simulation, and it will become very clear as I show you what the problem that we are going to look at today. As far as HFWorks applications are concerned, HFWorks is a product that obviously operates in the high frequency range. We pretty much cater to a few hundred megahertz all the way to a few hundred gigahertz wavelength range. Okay, so really the frequency of operation is very wide, and it's certainly in the high frequency space, certainly in the gigahertz, megahertz, hundreds of megahertz space. Okay, and you know, just by looking at this frequency of operation, it blends well with RF and microwave type of applications. Okay. So in HFWorks, one can do passive components, filters, couplers, multiplexers, etc. One can study the characteristics of your antenna design, both the far field and the near field solution. You can look at antenna feed networks, then EMI, EMC type of problems, EM field exposure, etc. So, and also HFWorks can also be used for signal and power integrity for your designs. So, and HFWorks ranges from wide variety of in the applications, as you see here, and also across wide variety of industries. So you can talk, certainly it belongs to the electronics world, but if you look at it, it also has applications in aerospace, in defense, in high technology, consumer goods, today with the wearable devices, etc. HFWorks is pretty much, and the Internet of Things, is really this product lends itself to a wide variety of industries and wide variety of applications. Okay. Now let's get to the topic of the day, which is something talking about filters. Now, I mean, as the name suggests, filters are passive RF and microwave components that basically filters some signal. So if you have a signal that has a lot of frequencies in it, a filter's job is to just pass certain frequencies that's of interest to you and block the rest of it. I mean, it's just as simple as it is. But these passive components are very interesting because the way they are laid out and the way they are designed determines how good the filter is, and what are the frequencies that it is going to allow to pass through, and what are the frequencies that it's going to block. Okay. Now, the key issues that engineers face while designing these filters is to compute what is known as the S parameters. They would like to understand the losses. What is the insertion loss? What's the return loss? For the frequencies that is of interest to them, they want these losses, the return losses, etc., to be as minimal as possible. And for the frequencies that are not of interest to them, they do want these things being reflected back. Okay, so the product helps you to compute these S parameters. The other thing that of interest to engineers is to look at the electric field distribution inside the model. Finally, one would like to look at the bandwidth. You know, it's just not one particular frequency, but how good it is operating in a range of frequencies. If, for example, between 5 and 5.5 gigahertz, how good is it doing? So that bandwidth is kind of important. And obviously filters can make up of multiple repeated components, as in the example that we will see. So it's kind of interesting. One would also like to understand at what frequencies this design would even operate. Okay. Now this is the cavity filter that we have today, and obviously the objective is to compute the S parameters and really see how this design of the filter performs within a particular frequency range. You notice here that there are many screws in the model. I have taken a section view here. Now the screws can be adjusted, the height of the screws can be adjusted, and the filter, the characteristics of the filter and the S parameters, etc., are very sensitive to the position of these screws. Okay, so if you have these screws going up and down, the behavior of the filter might completely change. So it's really important to understand, okay, various scenarios. Okay, what happens if I vary this the length of the screws, how much I tighten, and how does that affect? So we'll go over a few scenarios, and I will also introduce a great tool inside HFWorks called parameterization, where one can define any SolidWorks geometry or dimension as a parameter and use that towards your simulation. With that, without further ado, let me just jump into HFWorks to show you how the product looks. Okay. Now, this is HFWorks, ladies and gentlemen, but you know, it works right inside SolidWorks. As you see here, it's an add-in product to SolidWorks. So one can do your designs right inside SolidWorks, as I've done here. Here is an assembly of just one cell of my cavity filter that you saw here, in the image that I showed you earlier. Okay. Now the first step is I would like to get some understanding of the resonance frequency of this structure. Really, I mean, if what kind of frequencies will this structure really operate under? So to do that, what we do is we create a resonance study in SFWorks. Now, the way HFWorks works is each of the simulation is organized as a study, and one can do several different types of studies, as I mentioned before: S parameters, resonance, and antenna. For this particular starting point, I would like to understand the resonance frequency of this cell. Okay. Now you can make a guess about the lowest frequency. I know that this is going to probably work around 6-7 gigahertz, so I could make a frequency guess of 6 gigahertz, and I can create a study. Once you create a study, the next step is to define materials. Now you can easily define materials by go ahead and apply materials, and HFWorks comes with its own database of materials where you could select the materials to apply. In this case, the air region is made, and then the metallic regions are all made of some kind of a conductor material, something like a copper. Okay, so I have assigned materials to the components. Once you've assigned materials, the next step is to assign boundary conditions. Okay. Now, all the copper and etc., they are all implicitly IEC. It just means some kind of an imperfect electric conductor. Okay, so you don't have to really do that. That's why the name implicit. The program automatically defines all the boundaries which is in contact with the metallic substance, in this case copper. Okay, now there are two regions here, as you see here, two faces which comprise the air geometry, and this is where one would assign a boundary condition here. Now let me assign, pick the two faces, and then that is an imperfect boundary condition, electric conductor, and just assume that the surface conductivity, it's in contact with copper. So once that is done, I've already pre-solved this problem, and now let's proceed right into looking at the results. Now the results in HFWorks are organized inside what is known as the result table. Now as you see here, the resonant frequency is about 7 gigahertz or 7,000 megahertz. Okay, so HFWorks will be able to give you automatically the resonant frequency for your structure. In addition to that, one will also be able to compute things and look at things like in this case, say, electric field. Now this is the distribution of electric field inside the structure, and you could actually view it as a section plot, and you can look at things like electric field, etc., inside the structure. And now you will be able to appreciate how a simulation is really going to give insight to an engineer, because things like electric field, etc., exist, but they're really you can't view them with naked eye. It's really difficult. You can have probes to study them at particular instances in your on particular locations, but really to get a spectrum or view the electric field spatially, like what you see here, the simulation makes it possible and becomes a very good tool for engineers to do that. Okay. Now with that, let me go back. Now we know, just keep that in mind, that we are talking about a resonant frequency somewhere in the vicinity of 6 to 7 gigahertz for one such cell. Okay. Now we have a cavity filter that's made up of at least 6 of these kinds of cells. Now and you have screws that can go up and down, and this is the problem that we are really interested in. Now the first starting point that we use to compute the resonant frequency gives us an idea about what where this filter is really going to operate. Now I know this beforehand, but it's around between 6 and 7 gigahertz is where this filter really operates at its best. Okay. Now the next study that we will be doing is what is known as a S parameter study. So as I mentioned earlier, we have the S parameters, resonance, and the antenna. Now in the S parameter study, there are several different options. Let me just go over some of them. You know, you can parameterization is a very, very important concept here. Now any dimension that any of your geometry dimensions can actually be a parameter, and one can study how the solution varies as the dimension varies. Okay, so we're going to use parameterization. And as far as frequency sweeps are concerned, you can sweep at discrete frequency points, or you can do what is known as a fast sweep, where you can specify a particular frequency, and the program is going to extrapolate based on the results on that frequency how the behavior of the structure is in all the frequencies in the vicinity of the given frequency. Okay, so these are the different types of the S parameter options that you have here. So let me go back into the properties of the study that was created. So we are using parameterization, and we're doing a fast sweep, and I would like to sweep somewhere between say 6.3 and 6.8 gigahertz. Okay, with the expansion frequency point something around 6.55 gigahertz. So you are going to get many frequency points here, and the program will compute the results at these frequency points. Okay. Now with that, the study is complete. Once you define the study, the next step, just like how you saw in the resonance study, is to define what is known as the materials. Okay. Now the air cavity is made up of, here it's made up of air as the name suggests, and everything else is copper. Okay. So defining materials is extremely easy and simple in HFWorks. Now let's go to the boundary condition. Now this is where you define the ports. Okay, where is the signal going to enter? Where is the signal going to get out from? So those are what we term as ports. Now let's look at some of the port definition here. Now this is a port, as you see here, and you know it's activated by a unit power source, and here is a voltage point between the 2 points, point 1 and point 2. So this is how a port definition actually goes. Okay, and you pick the phase which corresponds to the port, and there are some properties with regards to how you want the port definition to be. Okay, now this is I would say one port, and in this filter this is a 2-port filter. So there's a second port, as you see here. You select the phase, you select the 2 points that really conform to the outer boundaries of the port, in this case what we call as the voltage points, voltage part, and that's it. Definition of port is extremely simple, as you just saw here. Okay. Once the port is defined, we are all ready to go ahead and run this problem. Now I do want to comment something. HFWorks is a 3D finite element type of a program. Okay, what it means is the HFWorks discretizes the geometry into finite elements. Okay, and this is made possible using what is known as a finite element mesh. Okay, HFWorks has automatic meshing capabilities. The meshing is smart and it's also adaptive. So HFWorks allows you to just don't worry about the mesh part of it. We take care of it internally from the program. So we allow you to view the mesh, so you can view the mesh. For example, here this is the finite element mesh. So the mesh is automatic and it's adaptive as well. Okay, now let me go ahead and hide the mesh. Now in this particular problem, as I mentioned before, we are talking about parameters, and each of these geometry parameters is, as you see here, the distance the screw is actually tightened. So I've got about 7 different parameters here, basically controlling the 7 screws, 7 of the screws that I have, and each of these is entered a particular starting value, and now I will vary these parameters, basically the distance that the screw is moved or tightened, and then we'll see how the response is to the changes in the parameter. Okay, and that's enabled by what is known as design scenarios. So now I can actually view the design scenarios. Now you can see here we have 4 scenarios, and in each scenario there are, each parameter takes in different value. Okay, so really this is how HFWorks makes use of design scenarios and parameters to do some exhaustive study that spans across all possible dimension values that one needs to cater to. As before, I ran this problem prior to this webinar, so let us go delve deeply into the results straight away. Okay. Now, what are the different kinds of results that HFWorks will give you? So we'll start with the result table. Now, in the result table, as you see here, this is the expansion frequency. You can get the generalized S matrix. So the S matrix is printed out for you. The normalized ones, the impedance matrix, and the VSWR. All of these things for each of the port is given to you in the result table. Now the next thing is, let's look at the plot, basically the S11 plot. Now we have 3 scenarios here actually, and here is a look of the S11 plot for the various scenarios here. As you see here, the red one, which corresponds to scenario 2, seems to do very well because it has a very low, this is in dB, it's a logarithmic type of scale, actually a negative logarithmic scale. So a value of -40 really means that it's a very little is being reflected, and this is a signal that goes through. So if you look here, scenario 2 with the right distance through which the screw is tightened, seems to be one which is behaving really nicely between 6.3 and 6.8 gigahertz. It has a very low dB, and they're all generally, and the bandwidth, as you can see, is somewhere between 6.3 and 6.8 gigahertz, where the average dB is less than -20 for scenario 2. And you can see how scenario 1 and scenario 3 fares in comparison with scenario 2. So if you were to pick a scenario for a filter that's operating in this frequency, you would like it to pass these frequencies, I would select scenario 2. So one can actually make these kind of what-if scenarios and study them inside HFWorks. Now finally, one can also take a look at the electric field results. Now here is a section plot of the electric field, and one can go ahead and animate this versus phase. For example, here is the animation of the electric field. As a function of phase. Okay. Now the port, HFWorks also allows you to study the port fields. Okay. Now you can look at it. These are the solution for just the ports, and you can see the port field vectorially for the port number 1, and one can also see the port field for the same port here. Okay, so so in addition to the magnetic field, electric field, one can also look at a 2D port field type of solution. So pretty much this this gives you an idea of what the product can do, how it is completely and seamlessly integrated inside SolidWorks CAD, allows you to quickly take your SolidWorks CAD geometry and simulate inside HFWorks. You can also do parameterization, where each dimension can actually be a parameter and can be simulated and studied inside HFWorks product. Okay. With this, I would like to just get back to the presentation mode and basically go towards answering some of your questions. Okay. So if you have any questions, feel free to enter it in your chat box, and we'll be very happy to answer them. Okay. Well, thank you very much. Thank you all for attending today's session. We look forward to seeing you in a one-to-one web demo. If you feel that you have some interest in this product and you would like to know more about it and how it fits your application, please feel free to contact us at sales@emworks.com, and we'll be very happy to give you a one-on-one presentation and do a customized web demo for you. And you can also learn more about the product by visiting the webpage www.emworks.com, and where you can learn about all our offerings and our product offerings and the different kinds of applications that we serve. You will also find white papers and from our customers, both doing RF and microwave type design, which you would find interesting. And last but not the least, you can visit our YouTube channel, where there are more than 60 videos which demonstrate the different applications and the different parts of the program. Okay. Yeah, there's a question about the need for SolidWorks. Okay, HFWorks requires SolidWorks CAD. Okay, now HFWorks currently is in HFWorks 2016 version. Very shortly we will be releasing our 2017 version. So HFWorks 2016 works with SolidWorks 2016, SolidWorks 2015, and SolidWorks 2014. So when we go to HFWorks 2017, you would require SolidWorks 2017, 16, or 15.
Okay, I guess that ends our webinar today. Thank you very much, Arvind Krishna, for the presentation today. And this webinar will be posted, the recording will be posted on our website starting from Monday at www.emworks.com/webinars. Thank you all, and you have a great afternoon. Bye-bye.